To Mathematical Proofs playlist. We'll be talking about variants of induction. So last video we learned about induction with our best friend Benny, and remember the idea of induction is that Benny needs to land on every lily pad numbered from 1 and so on. So first we show that Benny can land on the first lily pad, which is our base case. Then we prove our inductive step, that is showing that Benny can jump from any one lily pad to the next lily pad. And remember, the motivation we had to motivate induction itself is proving closed forms or showing formulas for summations. But that's actually very, very limited. We can use inductions in many, many different ways. Despite how rigid induction seems as a tool, we can actually adapt it in many ways to solve different problems. So let's go through the first example in your slideshow. So the first thing we're going to show is prime factorization. So we're going to show that every number greater than 2 is either a prime or can be factored into primes. And before we prove this, let's actually just run some examples. 2 is a prime, so no problems there. 3 is prime, good. But 4 is 2 times 2. So it's composed of prime factors, that's fine, right? 5 is prime and 6 is 3 times 2. That's 2 primes. That's fine. And maybe if you keep going on, you'll notice, hey, this seems like something that's true, but how can you use induction to make this work? Let's think about this. If we have 4, well, induction means that we use the last base case, which would be 3, but then 4 is 2 times 2. That doesn't really make any sense. So how are we going to use induction? There's actually 2 problems that you might be thinking of, and the first problem is not that big of a deal, and it's a matter of base case. We have to show that our claim works for every natural number greater than 2, but doesn't induction only work on base case like 1? You have to choose 1 as your base case. How do we solve this, right? But you just start at 2. This is actually one of the simplest things to do with induction. So easiest way to vary or change induction, you start at a different starting point. So instead of Benny starting from lily pad 1, he just starts from lily pad 2. So we can let our base case be whatever we want. But the main problem is this induction hypothesis issue. In regular induction, we're only worrying about jumping from one lily pad to the next lily pad. So we assume that our claim holds for k and we show it for k plus 1. But once again, the case of 4 relies on 2 being prime. So we need more than one step back. We can't just rely on the last lily pad. As you'll see, this actually isn't a problem. So let's actually look at a diagram here. So we're going to start with lily pad 2 and 3. Well, we know that they're good. So we're just going to color those in, make them darker, so we know these are good to go. Now let's look at lily pad 4. What's happening here? And you might see the dilemma. Benny can't jump from lily pad 3 to lily pad 4, but it doesn't matter because Benny can jump from lily pad 2 to lily pad 4. Clearly we were already covered lily pad 2 and lily pad 3, so it doesn't have to be the one below it. It can be any of the ones that Benny has been on. So Benny can jump from lily pad 2 to lily pad 4, and since he got to lily pad 2, since he definitely got to 3, there's no issues. See what's happening here? We're leveraging the fact that we've been on 2 before because of the fact that we know that we've been on 3. And 5's fine, that's not an issue since that's prime. Now we're going to look at 6 again. Remember? 6, okay, how are we going to prove this? Well, 5 is colored in, but we can't jump from lily pad 5 to 6. 4 is colored in, but you can't jump from lily pad 4 to 6. But 3 and 2, you can jump from lily pad 2 and lily pad 3 to number 6. And you need multiple lily pads. So there's a way of thinking that there's many, many different things that we're going to need from our induction hypothesis. So once again, you should understand, even if Benny needs many, many lily pads, and it's beyond the previous lily pad or the kth lily pad, it's fine because we were able to get all the way up to k. The thing about induction is that you solve 2, then 3, then 4, then 5. And it doesn't matter how you got it, but you know for a fact that once you got to that number, everything before is already true. And this is what we call strong induction. So strong induction is just regular induction, but there's one main change. The induction hypothesis doesn't just include the lily pad k, but every lily pad before and including k. So we can use multiple lily pads from anywhere before k. Once again, this is actually the exact same thing because since we got to lily pad k, we got to every lily pad before k, which means we can use all of that. We can leverage that extra information in ways that we don't do with regular induction. We're using all of the knowledge that we have. So now let's actually prove prime factorization. Let's just start. Our base case is going to be k is equal to 2, not 1. Our base case is going to be 2, and 2 is a prime number, so that's fine. Our base case holds. Now we're going to proceed with the inductive step. So then we're going to assume that every number from 2 to k is either prime or can be factored into primes for some random k or for some random lily pad k. Then we'll show that k plus 1 is either prime or can be factored into prime. Assume that every number from 2 to k is either prime or it's a lot, right? So what other people like to do is use this thing like p of k. So let p of k be the claim that k is prime or can be factored into primes. In this case, our base case would be that p of 2 is actually true. p2 is true. The inner induction hypothesis can be simplified to be assume P2, P3 all the way up to Pk is true, show that P of k plus 1 is true. So this is just two ways that you can think about the problem. We can either think about it directly or in terms of this P notation, which tells us, hey, P of this number, is it true or false? And we have to show that it's true for every single number. So remember, in our induction hypothesis, we're allowed to use every lily pad before k, not just the kth lily pad, because we're using strong induction. So let's consider k plus 1. If it's prime, the claim holds, since clearly k plus 1 is prime, the claim holds, or P of k plus 1 is true. That's the other way you can think about it. And if k plus 1 is not prime, then we'll divide it so that k plus 1 is equal to L times m. And remember, by definition, not prime means composite. So L and m is in between 1 and k plus 1. For example, 10 can be factored into 2 times 5, and both of them are greater than 1 and less than 10. But since both L and m are less than k plus 1, well, they already can be prime or factored into primes by our induction hypothesis, since every lily pad before k plus 1 is true. And it doesn't matter where it is. That is the interesting here. L and m can be anywhere from 2 to k, and that's fine. That's actually perfect, because the induction hypothesis holds for those numbers. Thus, k plus 1 can be factored into primes because L and m are either prime or can be factored into primes. Or in other words, using the P notation, P of m and P of L is true. And then you'll notice that this means that P of ml is true, which means that P of k plus 1 is true, since k plus 1 is literally L times m. Okay, now just to finish off our proof, since our inductive step is true in combination with our base case, every natural number is either prime or can be factored into primes. Or P of n is true for every single natural number. So here I provided two ways that you can think about this problem, or the inductive step, either directly or using this P of k notation for different values of k. And there's actually a name for this P of k thing. It's called a predicate. So for induction, you can either solve it directly or show that the predicate holds or the predicate is true for all of the natural numbers. And if you use the predicate path, that's fine. But remember, you have to define the predicate depending on your problem, so it's going to change. Okay. So let's just recap and think about what just happened. In our first problem, how do we adapt induction as a tool? Well, we changed the base case and we actually strengthened our induction hypothesis, leading to this development of a different tool called strong induction. And interestingly, both induction and strong induction are actually like, they're the same strength. Right? They prove the exact same things, but strong induction just gives us more information to work with. Technically, induction is strong induction, but only the kth lily pad, not the ones before it. So when you think about it that way, they're very similar and related. But we can actually still take this tool of induction further and change it in the following ways, which we'll highlight in the next problem. So show that every number greater than 2 can be written as a sum of 2's and 3's. For example, 41 is 11 3's and 4 2's. So let's convince yourself by doing some examples. I know that this next paragraph looks terrible, but just don't worry about it. 2 and 3 are fine, since 2 is, that's whatever. 2 is just 2, 3 is just 3, 4 is 2 plus 2, that's fine. 5 is 3 plus 2, that's fine. And 6, there's multiple ways to do this. You can do 3 plus 3, or 2 plus 2 plus 2, or 2 plus 4. And we already know that 4 is 2 plus 2, so that's fine. 7, exact same thing, 3 plus 2 plus 2. You could write this as 3 plus 4, since we know 4 is true and 3 is true. Or we can write this as 5 plus 2. That's fine as well. 8 is 4 2's, or 2 3's and 1 2, or 3 plus 5, or 6 plus 2. And there's a lot of information that's present here, but maybe we can see the pattern. We can use the previous steps to help on us. And in particular, like anything from 5 onwards, we can write as a previous number plus 2. So 5 is 3 plus 2, 6 is 4 plus 2, I wrote it as 2 plus 4, 7 is 5 plus 2, 8 is 6 plus 2. So you're like, okay, we can write every n as n minus 2 plus 2. And one thing you'll notice here is that n minus 2 is only 2 lily pads back. So we'll technically have to use strong induction, since we're not just relying on the kth lily pad. Even though it's just k minus 1 that we're going to be looking into, we still call it strong induction, even though we don't need everything from 2 to our number k. That's fine. So we're going to use strong induction here. And intuitively, we can go from lily pad k to lily pad k plus 1, because all we do is we take a number and add 2, add 2, add 2, add 2. And if we think about this logically, you're like, okay, let's reach every single lily pad. But as you'll notice, there's actually going to be a little problem here. We're going to put Benny on lily pad 2 and let him jump. So he jumps to lily pad 4, since you just add 2. He jumps to lily pad 6, so because you just add 2 and just keeps going. And Benny disappears off screen. Don't worry, there's no off screen death right here. But who's going to deal with the odd numbers? This is like, okay, what's happening here? What's really interesting is this adding 2 method, we kind of skip what's in between. So in here, we skip the odd numbers. So we're going to enter Tiffy. She's going to be the one that deals with the odd numbers. So we're going to place Tiffy on lily pad 3, and let's just get her jumping. 3 plus 2 is 5, 5 plus 2 is 7, and so on. And eventually, every single lily pad will be covered. And let's just think about what happened here. We notice that our induction hypothesis doesn't actually prove the next case, but the case after. Or if you want to show that a number can be written as a sum of 2's and 3's, you subtract 2. So you either subtract 2 or add 2. Or in predicate terms, we see that P of k implies P of k plus 2. And once again, what this means is that if P of k is true, or k can be written as a sum of 2's and 3's, then k plus 2 can also be written as a sum of 2's and 3's. But with only one base case, we actually only hit the even numbers. So if you imagine our base cases as frogs, one base case, Benny, and its inductive step, it's like k plus 2, will cover all the even numbers, while the second base case, which is Tiffy, will cover all the odd numbers. And what's really interesting here is that this is just a matter of base cases. So what we change is the fact that we can have multiple base cases. So let's start our proof. We start with the base cases. 2 and 3 is fine, since clearly they're written as a sum of 2 and 3's, so we can go with the inductive step. Now we're going to assume that every number from 2 to k can be written as a sum of 2's and 3's, or we can use the predicate notation to say that p of 2, p of 3, all the way to p of k is true, and our predicate is k can be written as a sum of 2's and 3's. And we're going to assume that this is true for some k greater than 3. If it's 2 or 3, then the base case will be true, so we're going to assume it for something that's not 2 or 3. So it doesn't really affect our proof, it just has to do with clarity. So now we're going to show that k plus 1 can be written as a sum of 2's and 3's. And, that's the same as saying that p of k plus 1 is true. So we'll just prove the inductive step directly. We have that k plus 1 is just the same as k minus 1 plus 2. And by our induction hypothesis, because we're using strong induction, k minus 1 can be written as a sum of 2's and 3's. So clearly k plus 1 can also be written as a sum of 2's and 3's. So our inductive proof holds, our induction holds, our inductive step holds, and the proof's complete. So the question here is, why a second base case? It's really weird because it doesn't actually seem like when you look at the proof we would ever need a second base case. So you could just be like, okay, can we just prove one base case and use strong induction? But intuitively, we know that we need Tiffy to jump on the odd numbers. So we're like, what's happening here? If we try to prove, let's say 3, the number 3 using induction, we can't, because 3 minus 2 is equal to 1. 1 is not written as a sum of 2's and 3's. Our second base case is actually literally what Tiffy does, make sure that the odd numbers work. We can't prove 3 by induction, so then we wouldn't be able to prove 5 by induction, which means we wouldn't be able to prove 7 by induction and every single odd number. Thus, we need to include 3 as a base case to be like, okay, this is our starting point. And this is why stuff like intuition is incredibly important, or understanding these things. Intuition makes sure that you understand all the small details to be like, okay, let me try to see what's happening here. Sum of 2's and 3's. Okay, you can think of the lily pad. Oh, there's like a gap in between. And some people who just brute remember everything, they might forget these small details, like, oh, I have to consider a second base case, because they're just like, oh, I'm gonna just use strong induction, it'll just work out. That's why when we do our proofs, understanding is really, really important. It ensures that we don't forget crucial steps and follow just a recipe blindly, and then we can also adapt what we know to tackle a slightly harder or a slightly different problem. And there's actually a small detail that we need to keep in mind here. In every single one of our induction proofs, we always say that, oh, we're going to assume that the claim holds for some k in the naturals. Or this is saying that Benny can reach lily pad k. And sometimes some people say, hey, let this claim be true for all k, or every single lily pad. What? That doesn't make any sense, right? Because that's literally what it means. If you assume it for every single number, that's the same as saying that Benny can reach every lily pad. And this is a trap that people fall into. But if you remember Benny, this shouldn't be an issue. So just be careful. Actually, that's all there is to induction. Induction is not too complicated. Maybe the questions in the worksheet will be a little on the tough side, but just remember Benny and the intricacies of lily pad jumping. So let's think about what happened in the last 3 videos. We learned about closed forms and the classic induction, and then we adapted induction to solve different problems. And the way we adapted induction is changing where our base case starts, using every or many lily pads before k, and thus developing the tool of strong induction and having multiple base cases. I think this is one of the longest ones we've done so far, so I will see you in the next one. Bye.